My name is Sally Cripps. I'm the co-director of the Human Technology Institute at the University of Technology, Sydney. And today it's my great pleasure to be talking to you about our special track session for the Data for Policy Conference in 2024 entitled Accelerating Collective Decision Intelligence. I'm going to begin by giving an overview, and then two of my colleagues, Gillard Francis and Roman Marchant, will talk about applications. We all want to tackle entrenched social disadvantage, and the question is, which policies should we implement to do this? And it's a very difficult question. And it's difficult because the decision landscape that's facing policymakers is rapidly changing and complex. Governments have finite resources. They cannot fund every policy. There are many stakeholders, many of whom have very different objective functions. The future is ambiguous and useful data is scarce. So what would policies look like that were able to operate in this environment? They need to be rigorous, explainable, and justifiable. They need to quantify uncertainty, and I'll explain more about why that is fundamentally important. They need to be agile and adaptive to cope with the continually changing world in which we live. They need to be able to combine multiple sources of information from not just data, but also from expert opinion. And most importantly, they need to reflect the values of those communities that will be impacted by those policies or decisions. So it's a pretty tall order in order to do this. What I'm now going to talk about is how to use Bayesian reasoning, particularly Bayesian Adaptive Trials and graphical models, in order to solve some really pressing problems facing policymakers. And the process starts with a question. And you'll see a question mark up there, and the thing underneath it is the letter theta, and that letter theta represents what we don't know. Now, for example, the federal government in Australia is considering reducing the intake of foreign students to universities in order to make housing more affordable. And so the question is, what will that reduction in foreign students do to housing affordability in Australia's major capital cities? So that's the question. How do we begin to answer it? Well, we start by saying, what do we currently know about the problem? And I'm not going to go through the maths, but that P, you can think of it as representing not just what is currently known, but also my level of confidence around it. It's what's called a probability distribution, and it measures not just what I think will happen on average, but how unsure I am about that. And those current beliefs come from many areas. They can come from experts, they can come from communities, or they can come from previous research. But again, key is the level of confidence I have in those current beliefs. And why is that key? Is because what I'm going to then do is, I now have my current beliefs, I'm now thinking about what extra data might I need in order to better answer that question. And what you're seeing up on the board there is an expression that says, I am going to gather the data which will increase my level of confidence or equivalently reduce my level of uncertainty the most. So that's a data gathering exercise. Having gathered the data, I then say, well, if I'm right about foreign students, the reduction in foreign students increasing housing affordability, how likely is it that I might gather that data? And that's called a likelihood function. So now we've got current beliefs, we've gathered data, we've got a likelihood function, and we're going to update our current beliefs with that likelihood function to give what's known as a posterior belief. So here I'm combining various forms of information from data and information from the current beliefs. This then feeds into a decision making. This says, in sort of complicated mathematics, that I'm going to make the decision that will maximise my utility. So for example, in the case of the housing affordability, I'll make that decision that I think will make housing more affordable to average Australians. That posterior belief now becomes my current belief, and the cycle repeats. Most importantly, this process doesn't just involve data scientists like myself. It involves the communities. It involves them by having them co-design, co-develop and co-implement the policies which they will be impacted by. And here is how the mathematics maps on to those elements of the policy cycle that I talked about previously. Quantifying uncertainty is absolutely critical in any decision-making process, and here we use it for that purpose, but also for another one, which is to figure out what we don't know to gather data in a smart way. We are working with the communities and experts, informing our current beliefs and also informing those utility functions. In other words, what does success look like to them in order to ensure that the communities are getting out of these policies what is important to them. As you saw in the previous slide, the methods are rigorous and explainable. This is not just a circular diagram, such as you would see in a management consultant slide deck. There is serious mathematics behind it. And we are combining multiple sources of information, not just information from data, but information from the communities and information from experts, and in particular, government experts who work in this area. So before I hand it over to my colleagues to talk about specific examples, to summarise, as digital tech and algorithms continues to advance, the adoption of Bayesian reasoning in social policy could mark a significant shift to better evidence-based decision-making. This shift is not just about adopting a new methodological framework. It represents a broader move to a culture of continuous learning and adaptive management in government for social good.
My name is Gilad. I'm a program director at the Human Technology Institute at the University of Technology, Sydney. And I'm going to talk about a use case for Bayesian learning for de-escalating conflicts, which we refer to as BLADE. And what do we care about? What do we need Bayesian learning for de-escalating conflicts? Managing and de-escalating conflicts is probably the most intractable problem currently in the world. And by understanding the drivers and mindset of actors in a conflict from ambiguous data is the key for assessing and evaluating different courses of action. Unfortunately, as you can see from the quote from the former US Secretary of Defense during the Vietnam War, this type of analysis often lack the mathematical rigor. And this is not unique for the Vietnam War. As you can see, there are various historical events and conflicts that were exactly suffered from the same issue. What we try to achieve is a robust decision support system that allows a decision maker to combine information from multiple sources, which means data from, let's say, intelligence, but also knowledge from experts, into competing hypotheses. These competing hypotheses allow the decision maker to value and weigh in different alternative courses of actions, weigh in both the consequences of an event versus its likelihood. And by doing so, we are acknowledging the uncertainty in the data and in the model. Our model here, BLADE, is a let's call it a simpler version of that, where we model interactions. So, for example, we take the Sri Lankan Civil War and we use publicly available data to represent various events and action taken by the government and the Tamil Tiger during the Sri Lankan Civil War. And from that data, what we are trying to capture is the interaction between them. We represent this interaction through a graph. One example of this is given here. These graphs provide the decision maker with a way of learning the cause and effects of what exact action lead to the corresponding action from the adversary. It allows them to quantify uncertainty, so a measure of confidence. How sure are we about these type of interactions? And lastly, it allows the decision maker to be transparent and explicit. These are transparent and explicit models. We know exactly what it means, and it's easy to interpret. So the holy grail of conflict modeling is a system that takes the BLADE concept but expanded to include other factors. Factors such as contextual factors, as economic factors, or actor-specific factors, for example, the demographic of a specific country. By doing that, we actually can present a different causal model that can explain the unfolding situation. And we do that with a rigorous mathematical framework. We can see here as with this equation that capture the different dependencies and the probability that we should assign for each one of those. This mathematical framework provides the decision maker with an actionable, and explainable model. Unlike the traditional black box model that we don't know exactly what's happening inside, this is completely transparent. And more than that, it quantifies the uncertainty about the model. So the decision maker can know how sure are we about this data and these models. And with that, we offer the decision maker with a robust decision support framework to de-escalate conflicts.
Hi, my name is Roman Marchant. I'm an associate professor at the Human Technology Institute at the University of Technology, Sydney. And today, on behalf of all co-authors of this paper, I would like to tell you about Bayesian causal discovery for policy decision making. The motivation for our work is to be able to alleviate the big assumptions that are being made regularly in policy decision making when assuming direct relationships between what are usually referred to as factors or independent factors affecting a single variable of interest or an outcome. Techniques like linear regression, logistic regression, and even neural networks are not able to understand the complex and intricate relationship between these variables in the same way as other more complex modeling strategies might be able to. Furthermore, there's usually an underestimation of the risk associated with decisions based on most these assumptions, but also on the lack of uncertainty quantification in this type of models. The contributions of our work are to be able to bring together both Bayesian causal discovery and Bayesian inference with policy decision making by making use of these techniques to both understand causal pathways from observational data, but also to be able to quantify uncertainty in the space of graphs, therefore providing a risk-aware decision-making landscape so that policy decision makers can understand the uncertainty and predict what the outcomes are of specific interventions in the complex relationship of the variables of interest. But what is causal discovery in Bayesian networks, and how do you achieve that? Well, there's three logical steps that you need to go through. First, you need to figure out what are the important variables. And for that, collaboration with experts and domain academics and domain experts in the areas of interest that you're working on is fundamental. Following that, and this is the most challenging aspect of causal discovery, is figuring out how these variables are related to each other and how can you quantify the potential causal relationships between them. As you can see from this table, the number of possible graphs grows super exponentially based on the number of variables that you have on the graph. Therefore, conducting a full exploration of the space is not possible. That's where techniques based on Markov chain Monte Carlo can help us better understand how can we efficiently explore this space to find the meaningful relationships in the data. Finally, once we know what the structure is, we can estimate the value of the parameters and then understand what the causal effect of different interventions are. In terms of experiments, we've conducted 2 experiments to show the benefits of such model in synthetic and real-world scenarios. In the first setting, you can see that we've simulated data from the bottom right graph in the slide. This graph is not a single output and multiple related input variables such as a linear regression model, but it actually shows more complex relationships in the variables or factors. These complex relationships are captured by a partition MCMC algorithm that is able to estimate the relative probability of each possible graph, better identifying the decision-making landscape, and most importantly, identifying in a much more accurate way the pairwise relationship between variables and other approaches. This means that even though there are multiple graphs, which you can see on the bottom row, there are multiple graphs that are identified as possible candidate solutions with equal probability, the fact is that all these graphs are what are called equivalence classes and allow you to then understand, the risks associated with different deployment of specific interventions. The important point here is that by being flexible around the relationship between the variables and uncovering through Bayesian causal discovery what are the most probable graphs, you're able to recover a true data generating process, the complexity of a true data generating process by fitting this type of more complex models. We've also tried these algorithms on real-world data, particularly on the longitudinal survey of Australian children. Here, we've noted that there's a complex relationship between factors, and it's no use to assume that, for example, if you're trying to understand school attendance, all the other variables in this model are equally affecting this outcome. You need to understand the complex relationships and what is potentially causing what. And these are what these algorithms allow you to do as well. So here in this slide, you can see the result of this is the most probable graph. Now remember, we're not only finding one graph, we're finding a probability distribution over them. And this graph is the maximum a posteriori, which means is the most likely graph given the data that we observed and the prior beliefs around what are the variables in this graph. This most likely graph, or maximum a posteriori, will tell us what are the relationships between all these variables. And we like to talk about this as suggested causal relationships, because in true sense, causality cannot be proved until you have an intervention, whereas these graphs are based on observational data and therefore suggest causal relationships. Now, what is the importance here and relevance for policy decision making is that you can now identify, for example, in the case of improving school attendance, you can identify the relationship between proximal variables, such as school enjoyment or general health, and identify where the root causes of potential problems might be coming from. For example, you can immediately see the importance of sleep patterns and sleep problems and how that affects, in turn, school enjoyment and general health. Furthermore, even up the chain, you can see how the financial stability of a family and parent employment can potentially then ultimately affect educational outcomes as well through sleep in general health and school enjoyment. This is an example of how these models can help policy decision makers identify at different levels in the hierarchy what the possible interventions are and what their effects might be. By using Bayesian causal discovery, you can then learn these complex relationships and understand the risks associated with your decisions and understand the complex relationships between these variables. In conclusion, by combining Bayesian causal discovery with expertise in domains and building these causal graphs, you can identify the suggested causal relationships between variables to then continue and conduct interventions that allow you to incorporate interventional data to better understand the landscape that you're working with. Policy decision makers can then now not necessarily assume that there's one single outcome variable and a few set of independent ones, but actually model the whole system in a complex mesh of relationships through these Bayesian networks to better identify what the levers they can pull and what the effect of these outcomes will be. Thanks for listening.